Let's look at solution history. Now, what we mean by solution history is making sure that we keep track of everything that we've done to a solution so that we could determine the concentration or amount of our substances that are dissolved, our solutes, in any one of the particular flasks or solutions. Now, why is this done? Well, we can do this to keep track of a serial dilution. That is, we take a solution and perform a dilution on it, and then accurately create a new, bigger volume, and then we may take some of that solution and perform an additional dilution on it to achieve an even more dilute sample. Now, this is done in stages, so it's called a serial dilution because you take one solution, dilute it, and then take that diluted solution and perform another on it. And this can go on as long as you prefer. Now, we need to keep track of all of the volumes that we use. So in this first case, we've taken 10 milliliters, perhaps using a pipette, and added it to a 100 milliliter volumetric flask, diluted it, properly mixed that solution, and then we've taken another 10 milliliters using a pipette, put it in a volumetric flask, diluted up to 100. Now, these volumes could be any volume you choose, and keeping track of those volumes will be important to maintain the history of that solution. Because sometimes we would want to calculate what the concentration of this solution is from a known concentration here, and sometimes we'll be measuring the concentration of our solution in the end, and we want to calculate backwards to determine the concentration of the original solution. So it really depends on the application. Now, I've found that it's usually best to limit the dilutions to a factor of 10 for each step. So, for instance, taking 10 milliliters and diluting it into 100 is a pretty accurate way to perform this. But if I were to take 1 milliliter and put it into 100, yes, that would have the same result as going from this solution directly to that one, but I often find that it's difficult to mix that solution well, and it's difficult to maintain the accuracy, and sometimes it's just a little bit too much. So it's better to do it in multiple steps. Now, why would we do it in multiple steps? Well, that's so that we can accurately perform a dilution without using lots of solvent. So by doing it this way, we minimize the amount of solvent and chemical waste that we would produce, while also maximizing the accuracy for this method. Now, you may perform dilution calculations using the formula M1 V1 equals M2 V2, and I've done that before too, but I find that actually using a dimensional analysis for the calculations is often better. And one of the ways that you can see this is better is when we do multiple dilutions, we can do it all in one dimensional analysis problem. And also this ends up working out quite well when we move over to doing our calculations on spreadsheets, which is the way I prefer to do these calculations. Especially since if I were to make a mistake somewhere in the calculations, I can just go back into my spreadsheet, change the one value, and it will propagate that change throughout the spreadsheet, simplifying the calculations, making it a lot faster. So let's do an example using dimensional analysis to calculate the concentration of a solution. And let's say this solution right here is 2 molar in chloride ion. And I want to know what the concentration of this solution is in chloride ion. So I've taken 2 molar, so I'm going to start with that because that's what I know. And I'm going to say 2.00, because that's what it is here, moles of chloride over liters. So that's what molarity is. Now I'm going to take this and I'm going to multiply by the amount that I pipetted out of this solution, because this volume is connected to that solution. So I'm going to multiply by that. And you'll notice that when I do that, my liters or the volume will cancel. Now you might ask, why did he leave the milli on there? You'll see in a minute, but we can do this. It just ends up that the units that I get out when I multiply these two things together will be in millimoles, because the milli doesn't have anything down here to cancel with, but the liters do. So milli stays, liters cancel, I'm ended up with millimoles. And what this set tells me is by taking 10 milliliters of this solution, which is 2 molar in chloride, I am now transferring 20 millimoles of chloride into that flask. Well, I now want to calculate what the concentration is in that flask. So I am going to take a millimole and divide it by milliliters. And if I do that, divide it by the concentration or the volume of this flask, I will then get the concentration in that flask, right? Because I know I've transferred 20 millimoles of chloride into this flask. I divide by the volume, then I'll get a concentration back out. So I'm going to do that. And I'm going to do that all in this one little step right here. Now you'll notice that when I do this in milliliters, now the millis will cancel out. And I'm back into molarity, because I've got, originally I had 20 millimoles on top. I divide by 100 milliliters. Then the milli in the millimoles cancels with the milliliters here. And now I'm into a molarity again. But that's not the end of what I'm actually doing here. I take 10 milliliters of that solution and dilute it into 100 here. So I'm going to do the same step over again. I take 10 milliliters of the concentration that I now have, and I place it into a 100 milliliter flask. So again, I'm dividing by the volume of the solution that I want to calculate for. So, and if I do this math, then I will determine the concentration of that solution. Now, this ends up being just simply dividing by 100. So now, this was a very simple example, and for the most part, we get to choose which volumes we use when we're trying to make a dilution. So when possible, I like to keep the numbers as simple as possible. So that way I can think, oh yes, that is the correct concentration there. That's what I would expect to happen. And if we're designing these properly, it can be a simple operation. Now, I mentioned that you can also determine the concentration of a solution over here and go back. So let's look at an example where that is the case. So let's say I have a sample that has copper, and we dissolve that sample in nitric acid, or we add nitric acid to dissolve the copper. And when we do that, say we have some soil sample here, we put it into our flask, we add our nitric acid to it, we get it all dissolved. We may add a little bit of water to it after the reaction has happened. We'll filter that to remove whatever other material is in there, and we'll transfer that into a 100 milliliter volumetric flask and dilute it to the mark. So now we have a solution that has presumably all of the copper that we had in this sample, but it's now contained in here. And since this solution is too concentrated for the method that we want to use, perhaps we're using atomic emission spectroscopy, which often requires very dilute solutions, then we will dilute the solution. So first we take 10 milliliters of that solution and dilute it into 100. And we do one more dilution where we take 20 milliliters and dilute into 100. And after we do all of that, we measure the concentration of this solution is 4.72 parts per million in copper. So now the question is, what is the concentration of copper in this flask? Now, all of this other part isn't really important for measuring the concentration in this flask, and even the volume of nitric acid was not actually that important. Just it's nice to use a fairly consistent amount for when we're preparing our standards or whatever other part of the method we're using to determine this concentration here, just so that we keep a relative same amount of acid in there, but sometimes it doesn't matter that much. Okay, so let's first calculate the concentration in this flask, and then we can discuss what we could do with that number later. So we start off with 4.72 parts per million. And another way to write parts per million is milligrams per liter, or at least it's close enough to write that. And so let's go backwards through our dilution. So this concentration corresponds to my solution in the 100 milliliter flask. So I need to multiply that by 100, because that will tell me how much of my how much copper was contained inside that entire flask, because that entire flask came from 20 milliliters of solution. So when I'm going backwards, I have to consider that. Since the concentration of 4.72 parts per million is of the 100 milliliter volume, that's what I use. So now I'm going to do 100 milliliters. Now when I multiply these two together, I'll get some weird unit because I've got a milli here and I've got a milli there, but we're going to use milliliters here too, so they'll cancel out. So don't worry too much about it. And by weird unit, I just mean, well, it would be micrograms, but don't think too much about that. All right, so here's the 20, and I want to know what the concentration is in this flask right here. I took 20 milliliters, put it in there, so I'm going back into the 20 milliliter volume. So there we go. There's the concentration in this flask. Now I want to go from here back to there. To do that, I multiply by the total volume of this flask, which is 100. And then I'm going to divide by where that came from, which is 10. Because I want to go in this direction. Now, when I do that, I get an answer that is 236 parts per million copper. And that's the concentration in this flask right here. Now, if I want to do something with that, like take it all the way back to this soil sample here, which is probably the case, then I will want to multiply that by the volume that's contained in this flask, and then I'll have to perhaps use how many grams of this sample I used, and I could calculate a percentage, or I could even calculate the number of parts per million of copper in that sample. Whichever I want to do, but this video is really about the serial dilution part. So very briefly, I can go ahead and do that though. So here's the concentration in that flask, and since I have it in a 100 milliliter flask, but in this case I actually want the units to cancel out, so I'm going to go ahead and convert that into liters. Hope that's not too confusing to do. Then the liters will cancel out and I'll be into milligrams, and it turns out that my soil sample over here would have 23.6 milligrams of copper in it. And then from there I could take the mass of this and calculate a percentage or something. I didn't note what the mass was. That would be important if we were doing an actual analysis to do. But notice something that isn't important. This really never comes into play when we're calculating the concentration of the copper. It's only important that we add enough of it that we're guaranteed that all of the copper has reacted. And this is likely far beyond what we would actually need. But sometimes it's important just to add a little extra just because we might be impatient and we want to force it to go quickly. So that's a little bit about solution history and how you use it. And that's also how I like to calculate it using dimensional analysis instead of a standalone formula. The other advantage of using dimensional analysis is that it would allow us to incorporate stoichiometry steps in there, or whatever other types of calculations we would like to employ. So it's a very flexible way to do that.